enjoy it. So it's going to be about the interactions between statistics / learning theory and optimization. So in the recent years, those interactions are really gone both ways, right? So statistics and learning have provided a new set of problems for optimization people, and in the other way around, the optimization algorithm and proof have given a new perspective on learning and statistics results. So we will see examples of both of these directions, and sometimes we need to think about both the statistical and the optimization point of view together. So we will see all of that during this week. One important thing that I want to say is that we have an open problem session on Thursday afternoon at 3:30 p.m. And I and the other organizer really would like this to be a success. So we will put together a Google document. You will receive an email with the link, and when we have the link, I will write it up on the board also so that you can sign up. So just put a title for your open problem and your name, and we will put together a schedule. So we are not interested in incremental problems, like the last line that you put in your paper. That's not the problem that we are looking for. We're looking for something maybe a bit bolder, a bit different from what you have been doing in the past. So I and we understand that you can be worried about credit in those cases. So the understanding is that if you mention an open problem, and somebody is interested in working on it, he will reach out to you and try to work with you. In the case that 6 months later somebody solves it by himself, then if you were not included, he will amply credit you, maybe put your name in the title or something like that. So really don't be shy about giving good problems. Okay? We will try to work together on it. Okay, so I think that's all I wanted to say, and I'm very happy to have to introduce Yinyu for the first talk, who is going to talk about robust stochastic and online optimization. Yeah.
Thank you. So my name is Yinyu, and thanks to organizer Sebastian and giving me this opportunity to talk about some of the work in the connection between uncertainty and optimization. I'm also use these fancy words called data-driven optimization. In fact, any optimization problem should be data-driven anyway. So I'm associated with Stanford University and ICME and MSE. So this is my outline. I just wanted to say, give a very brief introduction. What is the distributionally robust optimization? All this is the underlying and the stochastic optimization with data come from uncertainties. Okay, so and then I'm pretty quickly talk about DRO and the moment and some kind of a likelihood bounds. Okay, then I'm talk about the price of correlations many times. And we don't know what's the distribution. We just assume all the random variable are independent. So what price you can pay, and so for what kind of optimization problem, that's actually is the safe assumption, whatever. Then finally, I'm talk about online linear optimization, and also related to dynamic learning. So all this relate to some kind of a stochastic decision estimation optimization problems where actually you don't know precisely what distribution would be. So you relax that, and then hopefully you still make safe decisions. Okay. The whole goal is to try to develop some tractable and provable models and algorithms and with uncertain online data. So that's the theme of the work. So let me give a very introduction. So all this doesn't matter what's the estimation or optimization decision problems. So typically you face something and your decision variables plus some kind of uncertain data. Okay, here I call it C, and what we do is we typically assume and the C comes from certain distribution with the distribution functions. Then we take expected in the value. So this is typically, and in the old days, all people is like inventory, supply chain, and all the data estimation. So we do this kind of a stochastic optimization. Okay. we assume this decision variable comes from some kind of a decision space, we call it capital X, and C represent some random variables, okay, with this distribution. So this is has been used for many years, and the expected value is good measure of the performance, okay, but the cons is one has to know exact distribution and to perform this stochastic optimization. And from zooms, however, if the distribution, the underlying distribution is wrong, then you have a garbage in, garbage out. So this is problems, okay. In many practical applications, you may not know exactly what's the distribution function. In other ways, to do this is completely so-called robust, okay. So you minimize XS, so you just finding what's the support of your uncertain data, then you assume your adversary just choose a single point distribution, and to minimize this function, you want to maximize. This is change the settings to maximize. Anyway, so this is kind of a game, kind of a models, which we usually call robust. Okay. So this is robust to any distribution, okay, because you just pick a single element from this support set such that this function is minimized, okay. The cons and these were too conservative, okay, usually, and many statistical information and data behavior which is not utilized, okay. So this has been, and many authors is already talk about this is too conservative, whatever. Okay. So here comes to the middle ground. So in practice, we may not know distribution, but we do know some kind of samples or training data or statistical informations, measurement, estimations. So how would incorporate those information to build this kind of intermediate approach, okay? So between stochastic, which is could be too risk, but also has no robustic, but also another extreme kind, you have this robustic optimization. So here comes what we call distributional robustic optimization. Okay. So what's the distributional robustic optimization? Called DRO. So what we do is we assume we don't know exact distribution what it is. Okay. But however, we may have some support or constraints on those possible distributions. So we minimize still expected value for any possible distribution in this D. Okay. Then we assume this is still kind of adversary, but now your adversary is not choose a single C to hurt you, but you have to choose certain distributions, and those distributions have some constraints. So this is called DRO. So in the past 10 years, we have been trying to analyze this model. At the time, we were thinking, should we call the statistically robust optimization or distributional robust optimization or something? So we decided maybe we just call distributional robust. So the question is, so how to choose D? Okay. So we have to choose in D. We have to say make the model to be tractable. So hopefully we can still solve faster and theoretical maybe in polynomial time and those kind of things. Okay. And also you do have a practical statistical meanings. And finally, of course, practical performance. Does that make sense? Okay. So there was many work come out. Of course, everything has a history. So this kind of approach actually for single variables was actually introduced by Scarf and analyzed the inventory problems, like news vendor problems. Okay. Then many analyzed sometimes this problem is not tractable when you have multi-variables. Okay. So we started working in 2007 to prove certain models can be solved in polynomial time. Then there was many ways to discuss how to construct the D, the possible distribution. If you have a likelihood distribution, you have a divergence, then you have, I'm going to list a few of these in the Wasserton ambiguity set. This is all achieved, and they also find a very rich connection to machine learning and this kind of things, game, Markov decision process. Okay. Then some on the mean and the dispersions. And we also, then this is a paper, basically consider distribution set, just assume they are independent. So instead of multivariables and instead of find the joint variance, they just forget it, they just use marginals and assume this is a product distribution. So we'll talk about some of this. So application in many areas, okay. I'm going to briefly mention some of these. So I'm going to briefly go through very simple and the so-called moment and likelihood bounds, okay. So what's the probability D? So as I said, everything comes down and on D. So given possible and sample variance, okay, given possible sample mean, so this is the model we construct for all the distribution. Of course, they have to add up equal to 1. For simplicity, just consider this as discrete, okay. So the expected value and the maximum mean, and this basically build a Euclidean ball such that the mean value cannot be divergent from mu0 too much, okay. And also the covariance matrix of the two distribution, and it should be less than some kind of a sample experience by some lambda 2. So the question is how to choose lambda 1 and lambda 2, those two scalars control how tight those distribution would be, okay. So this is a distribution. All the distribution has to be satisfied those constraints. Okay? So this is what this distribution set is defined based on support, okay, and also first moment and also second order moment constraints, basically. That's what it is. Okay. So the question is, given such a D, so we have this is a matrix inequalities. Basically, say this is a matrix has to be lesser than this lambda 2, could be a scalar bigger than 1, less than sample variance. So this simple means this matrix subtracted by this matrix is positive semi-definite. So it's like you can consider this as a matrix confidence intervals, okay? And this is just a standard confidence interval for multi kind of decision variables. So, okay, so now first on this D, the distributed models, which we'll talk about, can be solvable? Yes. And so this is the first theorems to handle multi kind of uncertainties, dimensional uncertainties, but however construct this distributionally robust model to prove the problem is polynomial solvable. Okay. Expect is the using some semi-definite programming and plus some other convex optimization technologies.
Sorry, what do you assume about H?
H?
The function you check with.
Oh, yes. This is a function which has a certain technical assumptions. For example, it's convex in X, some certain concavities in the C, and also maybe multiples and something. Yes. Basically say if we fix the C and the problem is polynomial solvable, and these uncertainties, the expected version also polynomial solvable. Yeah.
So a question.
Yes.
Does this theorem still hold if you choose two different sigma naught from the first moment condition and the second moment condition?
First moment. Yes, I think it's still true. Yes, you basically say these two zero may not be the same.
Not the sigmas.
The
is the same for the first moment. And
for this one.
Yeah.
Yes, I think it's still true. I think it's still true. Yeah, basically this is just a convex region, and this is just a matrix inequalities. If you use different matrix, I think it's still true. But here we just use the same thing because and variance. So then, okay, so this is the tractable. The second question is, does this confidence intervals on first or the second moment made the statistical sense, maybe related to questions? Yes. You just consider this, you assume mu0 and sigma 0, which is the covariance matrix point estimate, and estimate from the empirical data, for example, size M and C. This is a big C, it's just the support, it's bounded, okay? So you can choose R1, R2, then you can prove the true distribution. It is not in this kind of concentration with high probability, whatever. So that's just the standard. Basically, we extended the confidence intervals to matrix confidence intervals and with these matrix inequalities. Okay. So that makes sense. So here you control sample size. Yes?
The dimension of psi is what?
A dimension of the psi in this particular case is not dependent on the dimension size when you choose gamma 1, gamma 2. I have to go back to check as long as this condition is satisfied. Okay. So this is the so-called confidence intervals. So it's tractable. And also, test on many portfolio, whatever, and the experiment seems performing reasonably well. Okay, so this is the one way to use moment information to construct the D. Of course.
I have another question.
Yes.
So technically, you also get a lower bound, right? For
yes, that's right.
Can you handle that?
No, I will prove if you use that, that's the NP-hard problems. Okay. So basically say, we think we just further relax. Yeah, theoretically, your confidence interval and covariance matrix should also have a lower bound, correct. But as you have that ones, and you have the problem become NP-hard, especially for multi and C-dimensional. However, this basically we remove that lower bound and matrix inequalities, make them a little bit larger. The D, so it's a little bit more conservative, whatever, in some sense. Whatever. Good question, yeah. Of course, many ways, maybe not given by a moment, we just given some observed data, then we just define and see, again, probability measure equal to 1, and we construct some likelihood functions, okay? So this basically says the likelihood function has to be greater than some, again, adjust, level of confidence, okay? So this is, for example, you assume support uncertainty is finite. You only have n possible realizations. So you observed MI samples with sigma I. So MI would be your sample distribution. Okay. So the reasonable max likelihood functions would be just MI log PI. P represent your true the distribution for this possible n probability. So this is a sense. So this max likelihood functions, and it's greater than gamma, of course. And in practice, you adjust what's the gamma is reasonable tolerance, and to be less robust or strongly robust. Okay. So this is another way to do this. Okay, this is what's the. Then you can again analyze a lot of statistical related to divergence, and how to estimate by samples confidence on the true distribution. Use the empirical likelihood theory related to Owen and the symptomatic theories, and the possible extension to deal with also continuous case. So that's one way. Basically, given you have a finite realizations, you do distribution sample and the distribution, then you want the true distribution, the max likelihood to be on a certain level. Okay. So that's another way to do it. Okay. And also, there was another way, a third way, to what's called the Western and kind of a distance between two distributions. So this two distributions can be expressed as the minimum cost of moving one to other, which turn out if you use the L1 and the cost, and this is basically become a semi-definite linear programming problems. Okay. So in this case, and you basically say, and this is the sample distribution, the true distribution. You want this distance to be less than something. That this underline, this function actually is the minimum value of a linear programming problems. Okay, it's convex. This is basically by a couple of people, and especially Kong, and they have a finite sample guarantee. You can prove correct probability is high with n samples, big N. You can prove the true as n go to infinity is still unbiased, goes to 1. Okay, and then you also say this complexity again on the objective functions, convex functions. A lot of things happens, and you have the same computational complexity as the simple sample averaging approach. Okay. So yeah, this is just the moving. You can think about finite. Yeah.
What does it mean? DRO is in the same simple complexity class as the.
So basically, it says computational complexity is if SAA for that problem can be solved faster, this one also solve faster, but it's a little bit more conservative. So basically, computational time bound is the same. Okay. Specifically, this is suppose many people use logistic regressions. Okay. So basically, you have this form, and so basically, DRO suggests you use somehow in that first uncertainty set. It's called the ambiguity set. You meaning the soup of this logistic regression. Basically, assume logistic regression data have some uncertainties, and I believe, and then with n reduce actually and reach connection to this kind of a regularized logistic regression. I believe, and John also did work in this one. So they passed this. And this depends on what's the cost you're going to use and the different norm. You may have a different norm regularity. Okay. So anyway, so this is the trend. Sometimes instead just use pure stochastic optimization, you build a little bit uncertainty. Somehow it can richly relate to certain regularity and objective, which is popularly also used. Now you find a new interpretation. What means the regularized and the regression. Okay, so this is the summary, and although provide the solutions, okay, tractable, sometimes maintains the same computational complexity, which is stochastic. Presumably you know the distribution. Here you assume you don't know distribution. And it's very many problems, okay? So that's the DRO. It turned out to be and represent a lot for the decision problems, estimation problems. So now I'm going to talk about the price of correlation, especially high dimensional uncertainty. Okay. So this is particularly choose. So this is just some possible, for example, portfolio optimization problems, or could it be facility location where demand, so most of it occurred to some discrete optimization, and how to build uncertainty is certain discrete optimization. Facility location, but I have many demand. Demand is uncertain. Okay. Again, is here I'm particularly concerned about C is the very high dimension, of course. So common solution is again sample average, but however, when the size, the dimension of C increased, usually the sample size would be also increased dramatically. So this is theoretically, you can say dimension increased, sample size necessary to make accurate estimation is also increased exponentially. So this is we usually call curse dimensionality. Okay, so yes.
I'm sorry. The required sample size to do what?
To accurately analyze the moment and all the moment information, the mean and also covariance, those kind of things. Yeah. Okay. Yeah. Especially covariance. So then we basically say, well, this particular problem says, suppose I only know the marginal distributions. I don't estimate the covariance. So what I'm going to do is, I'm just assume the distribution So basically assume this is the product distributions. Okay? And so for product, basically I'm assuming the random variable independent. So I don't need to analyze the covariance. Okay. So we still maximize this with the P, okay? And of course, you don't know the joint distribution. Theoretically, you need to do all the joint distribution to understand, and this you find also joint distribution function, density functions. But here, so what do? We just product marginals. So what's the risk associated with assumed independence? Can we analyze risk in terms of the property of objective functions? Again, and what kind of functions assume independence is the safe? So here, I mean, basically, I need to, if you assume this is a normal distribution, you know the covariance. Generally, you just need to estimate the joint distribution level. And that's the sample size which I'm talking about. So we quantify this risk. It's called the price of correlation. Because we relax, we assume they're independent, then we have to pay some price, okay? So this is, we analyze, and for what functions, this price is not too high. For what function, this price, it is very high. So at least in practice, basically we know what's the question, problems. We know one is the safely, for simplicity computational, for when computable, can we safely assume this kind of a product distribution? Okay? So here's the definition. What's the price? I'm still use this distribution model. Assume X star is complex. This completely assume you know the joint distribution. Okay. Here I'm assuming you only use a product distribution. So basically say, and the probability for ij or whatever is just the product of those probabilities. Okay. Then we consider this. Okay. This is a max over all the possible distribution estimate at X star. So this X hat is the one only estimated at the joint distribution. So this is a minimize cost problems. So this number will be bigger than 1. Okay? Because I restrict only to joint distribution. So how high would it be? Depending on what's the objective functions. Or sometimes we call the correlation gap. Okay, it's the concept. Okay, so yes, good. Okay, so many stochastic, especially independent distribution, get approximate solutions. Okay, basically because they're much easier to solve. Okay, you'll be able to use SAA once you know independence. Okay, and also capture value innovation. So if we say we have a provable POCs are smaller, it's not too risky to assume independence. Okay, large would be, and assume you need really got to know the covariance between the random variables. So in the nutshell, we basically say if the function is submodular, then you usually need a small POC. If function is a supermodular, need to large POC. This is the supermodular in terms of the uncertainty variables, because your function is also part of this. Okay, so what's the submodular? So in some sense, you can think about this function for any fixed x is the function of c. Okay, so what's the submodular? It's basically economic scale. Okay, and in terms, you can think about this, the quadratic functions and the covariance. The joint, the derivative is less than the negative correlated among the random variables. Okay, so in this case, and you prove POC is less than e divided by e minus 1. So e just the natural number, 2.78. Yes.
Just so I understand, the uncertainty set here, the set of distributions, is all distributions with the same marginals?
Yes.
All.
Yes, all distribution with the same marginals. Yeah. So this is the distribution with marginals, and this now we just use the joint distribution. Okay. So this is bound. It turned out to many stochastic combinatorial optimization, and the uncertainty like demand for facility location, you can prove what is the submodular. Then what's the supermodular? Supermodular basically leads to a large POC. Okay. So it's just the reverse. They are positive correlated, all the random variables, if you think about it continuously. Okay. We can show by example, it's bound to 2 to the power n. The small n is the number of uncertainty dimension of the uncertainty. So that gives you a classification. What problem have a small POC? So you can use stochastic bottleneck matchings and all these kind of things you can prove, and it's actually submodulus. Okay, you can reduce this to even some simplified to simple convex optimization problems and deterministic problems. You can apply it to any norm. So I'm going to go through quickly. It's just a couple of applications to show it is possible. Okay. Okay, so we have a submodular, we have a small POC. Okay, how large is this territory can be expanded? Okay, so can you expand, for example, to fractional sub-additive functions, or even to sub-additive functions, additive functions f x plus y always left, f x plus f y, those kind of things. Okay, so we basically convert this. It turned out, and you cannot say too much beyond submodular. Okay, so you really need to get the very good joint distribution. So you can prove this is greater than square root of n if it's only a submodular. Even fractional submodular, you can also construct example to see the POC. It is great.
So the POC can be all the way up to exponential in n, right?
Yes, to the power n. So yes, I'm going to come back to that questions, and yes. So can we a little bit expand to this? So this comes from this so-called beta approximate cost sharing functions. So in that case, this is a function which is defined by economists, and in terms of the fair game, in the bargaining game. So they have certain functions on C. They call the beta approximation cost sharing. I'm going to give a different definition a little bit later on. Then the beta is characterized how large the beta it is. So if beta equal to 1, this is very good beta sharing functions. Then what you can prove is for any of these type of functions, you can prove POC is 2 times beta. Okay, so what's the cost monotone cost sharing is basically say you can think about the C1, Cn, different agent. So they have these cost functions. Okay, can this cost function be charged to participant 1n independently? It's like a sum up of these cost functions, such that the participant i's charge, the pay should be decreased as the demand for other participants increase. So this is usually called the fairness of the bargaining game. For a submodular function, you just charge the marginal cost. When you charge marginal cost, the cost add up could be more than the function itself, the cost function itself. So that's the beta magnifier, which we talk about. Okay. So if you be able to find such function, satisfy those properties, you want to find a beta which is as small as possible. So basically, can we linearly approximate those cost functions to each C1, Cn? So yes, this is basically in many stochastic optimization, you can prove, and some functions do have 3 approximate cost sharing, 2 approximate cost sharing, and then once you have that, we can prove POC is less than 2 times beta. Okay, yes. And so this is also is monotone, the beta theorem. Basically, POC is less than 2 beta. So in this case, we have 2 proof this, you can safely assume demand are independent in the facility location problems, then POC should be less than 6. For some other problems, standard for rest and network design problems, and you can prove beta is less than 2. This is also, it turned out this beta function can be also provide a lower bound. So I'm not going to go to sales. Yes, for photon modular function, you can prove POC also lower bounded by E divided by E minus 1. So that's what relates to the question. So many through these kind of functions, you can prove POC is greater than Z, standard is greater than 2. So there was some gap between 3 and 6 and 2 times 4. But it's just different by constant factors. So that can be used to prove POC also have a lower bound. Okay, so there was also application to some deterministic problem, prove this bound is tight. Okay, and so I'm going to go through very fast. Okay, so I'm give a quick summary of these points of correlations or correlation gap. Okay. Basically characterize the risk associated assumed independence in any stochastic optimization problem. Because we know any of this problem is the balance between the solution quality and also solvability, tractable or not. So this is one thing. But however, we can upper bound the use property of objective functions. So many of the problems you can do structural analysis, know these functions satisfy certain properties. Of course, there were still many open questions. Okay, here I'm only use marginals. Okay, is there any additional information should be and some correlation information should be used? Should I use broccoli wise independent and some one group can I partition variable into two group, and each group may have a joint distribution, but overall each group are independent. So just expand it. Here I'm assuming completely independence. Okay. So the question is, can we, how that depend on the block size and stuff. Anyway, so, so this is still some people analyze this. So I don't know how much time I left, Sebastian? 5 minutes. 5 minutes? 25. Oh, 25, good. Okay. Now finally I'm talking about online linear and dynamic learning. So this is all related to problems which solve linear programming problems, which are unknown distribution. Okay, here I'm just use the very simple examples. I'm teaching the management science, and somehow I have to use some very elementary example to illustrate what's the concept. So there was a failing. There was you sell goods, products. Okay, there was a fixed selling period, number of buyers, which is there were fixed inventory of goods. Customer come acquire bundle of goods and bid for certain prices. Okay, then your decision sell or not to sell to each individual. Okay, or you still want to maximize the revenue. Okay, so this is the one example. Suppose you have some goods to sell. Okay, this is the current how much item you have in the store. Okay, so the customer coming. I'm talking about it in these bid models. He said, I want to buy one pants, okay, one shoes, and one hat. Okay, I'm willing to pay $100. Okay. Second bid comes. Okay, they said, I want just one T-shirt, I want one hat, and bid for $30. Okay, so you basically say, should I award these bids or not? Okay, if I award this, okay, bid, I collect $100. Of course, my inventory reduced by 1 accordingly. So, what's this? This is packing problems. If you collect all the bids, you can decide solve 0-1 linear integer programming problems and stuff. Then we decide which one to give, which one not to give. Basically, on this problem. Okay. So this is the usual code. You can use LP relaxations. If you have 1, so each of these variable between 0 and 1 continuously. That's the LP relaxation. Of course, in practice, you can if you have LP solution come out from 0.9, then you can just flip you can randomly decide the 0.9 probability. You can input the x1 is the probability to sell and stuff. Okay. So you can put this and so-called offline and the linear packing problems, and you maximize pi t, xt. Pi t are those dollars, the bit. Okay. AIT basically is 0 or 1, indicate which item is interested. Okay. Xt is your decision variable, is 1. You can relax this. So this is LP problems. However, now we consider a streamlined version or online version of these problems. Okay? You only know B, which is how much items inventory at the very beginning. Okay? Let's say you also know overall how many customers will eventually come to the store. You have an estimate. Could it be time length, could it be estimated. Okay? You only know this information. You don't know any parts in pi t AIT. Okay? Information revealed sequentially. Okay? You correspond to objective coefficient. So T is information, including the pi, pay, and AIT you do. And once you have to make irrevocable decisions, sell or not to sell. Okay? So many people use, pi t come from certain distributions, and the AIT maybe have certain patterns. So we use that information, then we solve stochastic version. But here, we want it to be distribution free, whatever. There's no information on pi t and AIT. So the question is, can you still, how to maximize this revenue? Okay, so now we formalize with AITs between 0 and 1. You can always scale columns, scale rows to make that happen. We just assume pi t is greater than 0. There was no much distribution stochastic information related to the bit data. Whatever. The only thing we assume is they arrive in a rundown order.
Sure, but you know what they are ahead of time, though.
We don't know. Hey, they are fixed, but it's hidden from me.
Okay.
You can just draw it, they arrive randomly, whatever.
So you just don't want them to be adversarial?
Yeah, I don't want them to be adversarial, that's correct. Because if you want them to be adversarial, there's nothing you can do, whatever. So if you have easy pricing, easy sale policy, they put all high bid in the end. If you have a hard sales policy at the beginning, they put all high bid in the beginning. So there's not much you can say about these problems. So the only thing I'm allowed to minor service, I can randomly draw them without a replacement. Whatever. That makes sense? Okay. So here's that. We define this LP maximum value by any given A and pi. They are here. Suppose I know them, I can solve offline problems, so that's my maximum revenue. Okay? Now, if I have online algorithms, I code this online algorithm to be C competitive if my revenue under these algorithms average over all the possible permutations is greater or equal to C times these offline LP values. That makes sense? You know, this is an upper bound. There's nothing you can do about this. Whatever. So you just hope C will be very, very close to 1. Whatever. So the question is, under what kind of conditions you can, so C has a probability close to 1. So what kind of online packing problems, which is can be use this online platform to sell goods, rather than just called call auction. Okay. So, is that clear? Okay. So the problem is how to analyze the C, whatever. How we control about these competitive ratios. Okay. So this is there was no distribution, rather than just take all the possible permutations. Okay. I'm going to introduce one numbers. It's called B. It's the minimum among all the BI. If you remember what's the BI? BI is just the initial inventory on each goods. Okay? So here's the theorems.
Question.
Yes.
You can scale the BI every time, so the minimum is just a matter of what measure you use.
But here I'm going to, this A is already normalized in some sense. So BI is not normalized. That's a good question, yes. Yeah, you can always get BI, but here we assume the A, the largest number in A is 1. So it's not normalized. Each row is already scaled. That's correct. For any epsilon between 0 and 1, so there was no online algorithm for solving this linear programming which achieve competitive ratio C 1 minus epsilon if B is less than log m divided by epsilon squared. So this is a negative result. What is the M? M is the number of goods. So this is the combinatorial auctions. Okay. On the positive side, there was 1 epsilon competitive online algorithms. If B is greater than m log n divided by epsilon, so you just forget the log term, so m divided by epsilon. This is true for any n m epsilon square. So this is a universal constant. So basically say, basically say if one of the inventory is very low, it cannot achieve this 1 minus epsilon in the worst case, okay? Because we don't know any distribution. However, if each item after normalization, you have enough inventories, yeah, you can do an M, you can achieve 1 minus epsilon and still do online decisions. Okay?
So I'm a little confused why this result is actually, you don't want to state it as something which is uniform in A and B?
Uniform.
In A and pi? Right, so...
Yeah. Here, you say assumes...
What do you have this like? So when you wrote this, I was expecting to see something that was depending exactly on the sequence of A and pi's that you would see, right? That would be a motivation to actually fix them ahead of time and then just work with the permutation. But the result you have seems to be uniform in those guys.
No, this is exactly. I don't know any information about A and pi.
I know, but your bound does not depend on either what A is or what pi is.
That's correct. Only on this constraint. Only depend on B. That's the only information you know in advance. The quantity of B. I only know these informations.
I understand what the setup is.
I only know these informations. I know what's the total number of these. That's the only information you know about it. Okay. So besides that, a pi could be some pi very small, some pi very big. Okay. But only thing I'm assuming is they arrive at random orders. So I precisely want to state my result depending only on B, which is the decision, which is the information you know in advance. Otherwise, you don't know anything, whatever. Okay? So everything boils down to these conditions. So initial inventories. Okay. So this again, this ratio is, so you can design many different pi. Okay, as long as assume I can draw randomly, make these decisions. Okay, so that's why my initial value it is dependent. So this is for all the possible A and pi. Yes, I'm not saying for certain A and pi this problem is good. This works for all the possible A and pi, as long as A satisfies this condition and pi satisfies these conditions.
Does this theorem hold for the integral version or the fractional version or both?
For integral versions. For integral versions. Okay. This is for integral. So my reference. So you have so this is integral decisions revenues. So this is a continuous version. So you know C cannot be equal to 1. You already has to have some sacrifice, but here is incorporated into the information. So, you know, so the proof is is for full lective result is like you have M equal to 1. If you have an inventory level B, you can construct an instance OPT, which is equal to B, and it will be loss square root of B. So you will never, there was no algorithms. You always have a loss B. So this is 1 square root of B. So what happened, this is already known. It's like this for dimension equal to 1. This is a secretary problem. But here is how to do M. So the proof technique is construct this, and it's basically say, can we separate this into log M rather independent problems? Okay. So then, and if you can simplify for each, you have a log M separable problems. Each one have optimal value this. Then you can guarantee you have a loss, which is 1 minus square root log M square root of B. So log MB, that would be your lower bound, whatever. So the problem is how to split a combinatorial auction problem into log M. So basically, you have some kind of a master to sell and the items. It's like become a packing problems, okay? So this is a must-have item in order to achieve things. Then you fill in a lot of normal items such that they basically filled up into equal to B. So it's lower bound. Okay, basically give you. There's no algorithm you can achieve this. So divide it into B log M, and then you just fill some other small items, some orders. Okay, how to prove positive result? It's very constructive. Okay, again, because all the talk is how to construct a decision optimization model, where distribution is not known. Okay, so this is again we only use. So there was no information available, so you cannot use backward. Okay, so you have to use some kind of online algorithms, which we call the learning based. Especially when you learn, you have to also do. Okay, so what do you learn? The problem would be easy if there was some kind of ideal prices for each item. Okay, let's say this is ideal. Some magically, I know this is a very good price for each item. So when the first comes, I know the itemized price. So these three add up, 45, 45, 15, that's 105, 105, and his bid is 100, I reject. If this guy buy 2 items, t-shirt, $10, and has 15, he buy 25 of things, and he's willing to pay $30, then I say yes. Everybody understand this? Okay, online decision now. Once you know somehow ideal, okay, prices. Does that price exist? Yes, it exists. Once you collect all the orders, you solve these linear program relaxations. You find what's the due multipliers, which in linear program we call shadow prices. You can prove that shadow price would be ideal prices. The question is, you come from 0, 1, you still need to all the information in order to compute those shadow prices. Now what do we do? We learn those prices by using arrived information. That makes sense? Okay? So this is what we call the learning algorithms. Okay? So, and the price and bid, if you know the P star, then you can know. So basically, we approximate and we learn this shadow price. Do they have a concentration? Can it be learnable or something, whatever? This related to these questions. Okay, this is so-called one-time learning algorithms. Basically, I have epsilon. Think about this 1%. Okay, you have like 10,000 bidders and N. So first 100, you don't do anything. You just observe the data. Okay? Once you observe data, so you can use this as a sample. You formulate a small sample linear programming, hopefully very close to the population linear programming problems. And then you use that price, small sample linear programming shadow price, for your future decisions. Okay? Okay, so this is a very, okay. So this is what I said at P0s. So how much then you solve a small linear copy of a linear programming problem. Instead of give them full resources, you give them epsilon% of resources. If you forget this 1 minus epsilon things. That makes sense? Still xt between 0 and 1. That's my sample problems.
That technique would work for the secretary problem in a special case?
Yes. Yes. Here I'm giving a little bit smaller. That's because in the proving techniques, I need to, this estimate is not unbiased. So kill those unbiased estimate. I give a little bit 1 minus epsilon times epsilon. So instead, exactly 1% of resources allocated to this 1% of customers, I give them a little bit less. But the overall idea is, because I assume random permutated, right? The first $100 should be a good representation. I don't need pi, but it's a good 1%. Those 1% customer probably consume 1% resource. So I just give them 1% resource. I solve that for shadow price. Okay. Then the rest of the decision is easy. So that's one-time learning. You can prove. Again, I'm only faced my condition on B, okay? I'm not any possible A and pi, okay? So this is m log n divided by epsilon cube. In terms of m, it's the, this is m. So in terms of epsilon, this is not optimal, whatever, because all the lower bound indicate, depending on epsilon, should be epsilon square, whatever. Can we achieve epsilon square? Yes, this is called dynamic learning. I'm going to skip the proof idea, outline proof, okay? So this is so-called dynamic learning, okay? Why not? You update your price. So at the time epsilon n, you compute your sample linear programming. You use that price as decision. After you get 2 epsilon customers, 200 comes, you use that available data, solve a slightly larger size than linear programming problems. That makes sense? Update and 4 epsilon, so I'm going to update at this double 2 and power 2 phase. Okay? So basically, I'm give at each of these L, this place, I'm give these proportional resources, again, discount a little bit to kill the bias. And this epsilon is close to the epsilon squared to n divided L. L take epsilon n, 2 epsilon n, 4 epsilon n, the power 2 phase. Okay? Once we update the price, we use this. So you can see, we compute the initial price. We use that price to make an online decision. After you get 2 epsilon, and we compute the new shadow price, and we use this, and just for the rest of the case. So this is a poster. So here's, so then what do? We reduce this to epsilon squared, which is the optimal in terms of dependent on the epsilon. Okay? So I like this result because it shows which reasonable people probably do in practice. You want to, why not just within one time? So once you assume the more sample data comes, you should exploit this information. Okay. So again, this is the time. So I'm just give a little bit of history of these problems. We proved the lower bound, the upper bound. So for m equal to 1 is good, okay? There was some other unspecific betting problems which you need OPT greater than this, which you can get 1 minus epsilon competitive ratios. There was paper on both need to be greater than epsilon 3. Okay. The paper I talk about today is based on this 2010 work, so m log n epsilon square. If you still remember, forget this log term. Our lower bound is log m divided by epsilon square. Remember? If v is less than that, you cannot do that. But however, this gap, so there was another piece of work. In the following 3 pieces of work, which happened in the next couple of years, it turned out our lower bound is tight. You only need to be greater than log m divided by epsilon. I'm just omit some log term or constant term, whatever. Okay? So this is more like a one-time learning. So this is, as Elon had, this including the secondary problem as a special case. Whatever. Okay. So one time, most is the epsilon cube. I said dynamic learning, that's what we did. Okay. There was an extension to this one. But here I'm put a dynamic star. What's the dynamic star? Actually, they updated the price. In some sense, they update the price every time, whatever. Every new order comes, whatever. Okay, so we order at this power 2. We update those prices only at this power 2. So, but in some sense, they update more frequently. So, in some sense, the lower bound result, upper bound result. So this result only depends on B, works for any A and pi. Okay, and so it works. Okay. So I'm out of time now. Okay. Yes. Okay. I'm just quickly. So this is. We're also working on the so-called price post learning. The model I talk about is the bid price. The customer bid for a certain price. The seller decides to sell or not to sell. But in most real cases, is the seller decide what's the price, and then watch whether consumer buy or not to buy. Okay. So in those kind of things, can you still do something? So here I'm just quickly assume there was a lot of assumed distribution. Some use dynamic programming. But here, what we did, we just assumed the arrival is Poisson, but however, arrival rate, which is dependent on the price you posted. Okay? So the question is, we need to learn these function values. To sum short, this is non-parametric search. We don't assume the arrival rate function have any specific form. So basically, we build similar things. We can achieve the optimal learning rate. I'm going to run out of time. So basically, you have a regret rate. So we basically achieve a regret rate, which is minus 1 divided by 2, which considered to be the optimal one. So I'm going to, keep. Okay. So basically, the algorithm is basically post several price. So you can think about this is the section. Again, you have a geometrical pace to update, to try your different price. Then the confidence intervals, the optimal price is getting narrow, narrow, narrow. Finally, you get a very narrow price, and such that would be the price you learned. Okay. So summary. Okay. On this online optimization, lesser than sufficient now. Again, but however, as you said, maybe if we assume A and pi have a certain patterns, maybe this rate can be normal. So this is not going to be the lower bound, whatever. So that's one thing. Online on for a very general class of nonlinear is distribution free, or for the price posting, it's non-parametric. Okay. So I particularly wanted to advocate this dynamic learning. Okay, even this is one-time sales, but you can still break into multi-period. So you learn from the observed data. So we call learning while decisioning or do something. Okay. We still don't know whether this can be true for the buy and sell. Okay, market. So right now, the item maybe one narrow can. So right now, I only sell things. But maybe, presumably, somebody go to a platform and want to sell some goods to me. As the market maker, should I accept those bids or not? Okay. So then that would be a truly linear programming problem. So can you still say something on that one? Okay. And also multi-item pricing term stuff. Okay. More general online optimization. So we basically find out, and then the Lagrangian optimal Lagrangian multiplier, and then the shadow price seems a good thing. At least we have a target to learn. Okay. Okay. So I think, I think that's all I wanted to say. Yeah. Thank you. Yeah. Yeah.
We have time for a quick question or comment.
Yeah. Yes.
So you mentioned for submodular function beta was 1.
Submodular function.
Yeah, so you had this beta and 2 beta.
Oh, that's the cost sharing functions called beta. Yes, for that one, for submodular function, it's like a beta equal to 1.
So then you would basically hope to be able to put that 2 beta to e over e minus 1.
That's correct. We hope at least we want to prove even yes, we want to prove the beta, for any beta, we have e divided by e minus 1 beta algorithms. But right now, we're only provable for 2. That's correct, yeah. So yes, that's why for submodular function, you have, let's say, your objective coefficient C is uncertainties times your decision variable. So that's already beta equal to 1 cost sharing functions.
Maybe just a comment to connect with future talks. So the upper bound of the log m over epsilon squared, if I remember correctly, it's like online gradient descent or online mirror descent on the dual variables.
Correct, correct. It is like, so originally we used this kind of a double 2, power 2, because we're afraid solving linear programming is too costly from practical concern. Whatever. Each time you make a decision, you have to solve an ever-increasing size the linear program. But turn out that the shadow price can be updated. In some sense, it's just use the coordinate some kind of a descent algorithm to, given the previous price as the initial point, it's just update. Basically, you only have 1 data point added to the problems. Correct. Yeah, just update that price. It turns out that's not a major concern. It's computationally also super efficient. That's, yeah, very good comment.
Thanks again.
Okay, thank you.
So now we have a break and we come back at 11.
Yes.